Beth Biller, who's come over from Edinburgh University, the Institute of Astronomy. Beth is a world expert on exoplanets, and in particularly the very new field of directly imaging them. You've been around the world: Hawaii, Germany, United States, Arizona, and then for the weather you landed in Edinburgh. But of course you should have come to Glasgow. You're even better weather. So to tell us about weird new worlds, please welcome Professor Beth Biller.
Okay, so first I'm going to just start by telling you what it is you're looking at here. You know, in astronomy we get lots of fuzzy blobs. We find those fuzzy blobs very exciting. Other people maybe not quite as much. Oh, I think I need to stay over here. Can you hear me better if I'm right here?
Yeah. Yes.
Yes.
Yeah.
The microphone is right here, so I'm going to have to not walk. That's okay. We can manage that. All right. This is the first planet imaged by the James Webb Space Telescope. It's a planet outside of our solar system that we knew of before, but this is the first time we've imaged it, especially at these wavelengths. So this is the star, and this is a zoom in. The star is now behind the star. And after using the very advanced chronographic capabilities of James Webb Telescope, we can result this faint little planet here. So this is at about 3 microns in the infrared, 4.4 microns, 11.4 microns, and 15.5 microns. So the images kind of going from bluer to redder over here. And these two, these are the first images of planets outside our solar system taken at a wavelength longer than 5 microns ever. So this, however, is what we would consider a highly non-habitable planet. It's kind of like a baby version of Jupiter. So it's just formed, and the temperature at the top of its clouds is maybe about 1,000 Kelvin, so about the same temperature as a candle flame. That's one reason we can image it in the infrared. So highly non-habitable. Now I'm going to back up and tell you a little bit, how did we get here? So here we just have this fun graphic of the history of both solar system and exoplanet detection. So here we have just our 6 planets here, and here we get Uranus, and soon we'll have Neptune. Soon, come on. Now we're going to wait a while, and the problem is this goes very slowly and then it goes very quickly. Eventually we're going to have Pluto. It's going to go away, as you know. And now in 1995, we're going to see our first exoplanets, our first detections of planets outside our solar system using a technique known as radial velocity. And then we're going to start seeing exoplanets detected by another transit technique called transit soon. Yes, in 2002. This is going to start filling up very rapidly about 2009. That's due to the Kepler mission. I'm going to do it. Yes, there we go. We also have some planets that are detected by a microlensing. I'm not actually going to talk about that too much. And then now we also have a few directly imaged exoplanets. But what you're seeing is this just is filling up. Basically, anywhere we have the sensitivity to detect planets, we have. Except one place we don't have yet is here we have a period of 1 year, a mass of 1 Earth mass. And this area didn't fill up. We're still working on that, being able to detect planets like the Earth in other systems. So we're interested in this whole panoply of planets. But of course, we're particularly interested in the ones that are potentially habitable. So most of you have probably already heard about the concept of the habitable zone. So here we have the radius of the orbit of the planet relative to the Earth. And then we're going to consider the mass of its star. So Earth, not surprisingly, is right in the middle of the habitable zone. This is the zone where you expect to be able to have liquid water on the surface of the planet if it has an atmosphere. And we have 2 other planets that are very close to the habitable zone in our own solar system, but just a little outside, Venus and Mars. Now if we move to a higher mass star, it is bigger, it is hotter, and much brighter, and that pushes our habitable zone further out. Now if we move to a lower mass star, much smaller, much redder, much less luminous, that pushes the habitable zone inwards. So we actually have a bunch of habitable zone planets detected at this point, but they're mostly right here. So here's, of course, the artist's impression of what it might look like on the surface of one of these planets. So this is the artist's impression of what you might see if you're sitting on the surface of Proxima Centauri b. So it's actually in a triple star system. So here's its sun, Proxima Centauri, the nearest star to our own. And then here you can see two other stars. This is Alpha Centauri, A and B. So from the surface of this planet, you'd be able to see these guys as well during the day. So how is this detected? This was detected by this radial velocity method, which was the first method used to detect planets. And this is essentially looking at the tug of the planet on the star. So this is very much not to scale here. Essentially what's happening, we think of the planet as orbiting the star, but it's also tugging at the star and causing the star to also orbit around the center of mass of the system. Right, so the star is sometimes coming towards us and sometimes coming away from us as it's orbiting around the center of mass. And we can detect that if we look at spectral lines in the star's spectrum. So at specific wavelengths, atoms will absorb light from the star itself. And at the point of the star is moving away from us, those lines will shift redwards. At the point of the orbit where the star is moving towards us, because it's being targeted, it shifts them bluewards. So we can measure that shift in the spectral lines across the spectrum. And that way we can basically measure the radial velocity of the star as it moves towards us and away from us, which is a proxy for the mass of the planet. So for this planet that we're looking, have our artist's impression of what its surface might look like, this is what the data, discovery data look like. So this is the velocity of the star in kilometers per hour. The star has some just space velocity, so that's why it drifts this way. And then it's being tugged by the planet. So the amplitude of this curve gives us an estimate of the minimum mass of the planet. The period of this curve tells us the length of a year for that planet. So again, this is around a very small red star. It is in the habitable zone of its star, but that means it's much closer in to its star than the Earth is to the Sun. So you can see a year on Proxima Centauri b lasts 11 days, so very different than what life is like on Earth. So this is one habitable planet, and habitable zone planet, not necessarily habitable, that you've probably heard of. Here's another. So who's heard of the TRAPPIST system? Yeah, most people. So this one's kind of wild. So its star is just barely a star. It's really right on the edge. It is big enough that it fuses hydrogen to helium, but just barely. And it has 7 planets orbiting it. This is obviously, again, artist's impression. So how is this one detected? This is using this transit method. And the idea here is if you have the right geometry, where the planet is passing in between us and its star, it can pass in front of the star and block out just a little bit of the star's light over time. So this is basically, if you were looking at the star, as the planet passes in front, it will just dip slightly in brightness. And this is what we refer to as the light curve. So again, here's our artist's impression, and here's what we actually measure for these planets. So this is them passing in front of their star, blocking out a slight amount of sunlight as they do that. And the depth of this transit tells us something about the size of a planet. And how often these transits occur, again, tells us the year length of the planet. So 3 of these, the middle ones, are in the habitable zone for this tiny, tiny star, and that's basically ranging from about 5 to a 10-day year for this particular star. So again, very different than our own planet. So actually not those 2 planets, but now we have like over 5,000 exoplanets we know of, and most of those come from 2 space missions in the last couple of decades. So the first one, which I mentioned already, is Kepler, and then the K2 mission that followed that. It's actually a pretty small telescope, and it basically just kind of looked at one spot of the sky for 3 years. Its goal was originally to try to find an Earth twin, but unfortunately its gyroscopes failed before it could do that. But it still detected thousands of planets, so hey, that's a win. And then now we have TESS as well. So TASS is, instead of Kepler, which just looks at one point in the sky, it's actually scanning the sky, but it's also detecting tons of exoplanets, and especially more of these habitable zone, low mass star exoplanets. So here are some of the habitable zone exoplanets discovered by Kepler. Again, artist's impression. So this brings the question in, how do we know if these planets are habitable or not? And the answer is, we don't, right? So these were detected by a transit. So we've measured how big they are, and we've measured the length of their year. That's it. That's what we know about them. The ones that are measured by a radial velocity, we know how massive they are, which is not the same as how big they are, and we know the length of their year. That's it. So this is all extrapolation, and these surface features on this one, for instance. And there's some pretty interesting things you can extrapolate, but we don't actually know if these are habitable, and they may be very, very different than our own planet. So I've mentioned they're around much lower mass stars, so you've likely seen some of these NASA Travel Bureau posters. They're super fun. So this is for one of these M-star habitable zone exoplanets, Kepler 186f, where the grass is always redder on the other side. So this is a planet around a low mass star that's producing most of its light at red wavelengths compared to our higher mass star, which produces light all through the visual, but peaks around yellow or green. So while planets on Earth use chlorophyll to extract the most energy from the light we get from our sun, that might not be the best strategy on an M-star planet, hence why you might get something like red vegetation instead. So extrapolation, we don't know. There's some other problems too, especially with some of these M-star, low mass star exoplanets. For instance, a lot of them are tidally locked. One side of the planet is always facing the star. The other side is always facing away, so that might not be so great for life. But a bigger problem is that these low mass stars are very active. They're producing a lot more X-rays and gamma rays proportionally than our sun. So Proxima Centauri b gets 40 times the X-ray and gamma ray radiation than we do on Earth. So that's probably not good for habitability either. But we just don't know right now. So to really find out, we need to understand something about their atmospheres, well, even if they have atmospheres or not. And to do that, what we need is photons directly from the planets themselves. So this talk, I've been kind of talking about how we detect planets. Now I'm going to transition to how we characterize planets. Eventually, we really want to characterize habitable zone planets. We'll do a handful of those with the James Webb Space Telescope. But a lot of what I'm going to be talking about is how we can characterize somewhat higher mass planets right now using two different techniques. So transit spectroscopy, I keep on hitting this, turning it off by accident, which is an extension of the transit technique I've told you a bit about, and direct imaging, which is, let's just take a picture of the planet directly, hence we have light from the planet directly. So I'll start with transit spectroscopy. And first we need to do a bit of geometry. So we've been talking about the primary eclipse so far, right, where the planet passes in front of the star and blocks out a little bit of the starlight. You also get a secondary eclipse where the planet passes behind the star, right? So you can also, you can't see the planet during the secondary eclipse, but you can observe the star, and then the planet when the planet is in the eclipse, and then the planet when it's not, star and planet when it's not, subtract them. And you can also, you're going to see the planet at different phases. So here, we're kind of seeing a crescent planet, actually. This is the day side planet, and when the planet is passing in front of the star, we're seeing the night side. So you can also measure the phase of the planet from this light curve. So this is a fairly extreme example. This is a hot Jupiter planet. It's really close to its star, really big. One side is really, really hot, one side is really, really cold. Well, it's not actually cold, but colder. And this is looking at 3.6 microns, so with the Spitzer Space Telescope and in infrared, and you can see all of these features. So here is that phase curve when you're looking at the day or the night side or the crescent planet. And you have the deep dip during the transit when the planet passes in front of the star, and a much smaller dip when the planet is in eclipse. So now if you want to do spectroscopy of your planet, you have two ways of doing this. The first is you can use these eclipses, as I kind of mentioned already. So you wait and observe just the star during the eclipse. Previously, you might have observed the star and the planet, subtract the two, and you've isolated the spectrum of the planet. So this is something that we could do with the Spitzer Space Telescope previously, up until about 2019. It's something that the James Webb Space Telescope will also do quite well. And we'll start to see some more results from this soon. But most spectroscopy results you see from the transit method are using transmission spectroscopy. And this is actually essentially measuring the size of the planet as a function of wavelengths. So if you look at different wavelengths, some wavelengths of the planet will look bigger, some wavelengths of planets will look smaller. So the planet looks bigger where you might have an absorption line. So here, the atmosphere becomes optically thick, not as far down, so the planet actually appears bigger in this absorption feature. And here, when you're not in an absorption feature, the planet actually will appear smaller. So you can figure out where the opacity is in the atmosphere as a function of wavelength by the size of the planet that you measure at different wavelengths. All right, and here's what some of these spectra look like. So these, again, are hot Jupiter planets. So very close to their star, very hot. And don't worry about what it says on this axis. This is basically how big the planet is. We've just shifted all of these different planets off of each other so we can see them better. So they're just shifted relative to each other. And I'll just note a couple of features. Like, so we have a very strong absorption line in sodium and in potassium. And you can see there's these little spikes in the planets where they actually appear bigger when you have this absorption feature. And here we have kind of a broader absorption feature from water. It also causes some increase in the observed size of the planet at those wavelengths. So this is how we do most exoplanet spectroscopy with current instruments, although that will be changing. Let me show you one more example of this. So artist impression again. This is not a hot Jupiter. This is actually a super-Earth planet instead, a kind of planet we absolutely don't have in our own solar system. So around a low-mass star again, but really close in, really hot, kind of in between Earth and Neptune mass planet, and it has very cloudy skies. And how do we know that? We know that by taking a lot of time with the Hubble Space Telescope and looking at its atmosphere. So this is a bunch of different spectra. So the first spectra taken here, these gray points, those were taken with the Hubble Space Telescope initially. And the spectra, again, just looking at, this is essentially the size of the planet, the transit depth, as a function of wavelength. And this team then fit a couple of composition models here, what they would predict for various compositions. So if they had solar composition, this is what they should have seen, the orange line. It's clearly not a solar composition. If this was 100% a water world, just a chunk of water, then it should be the blue. And so we can't really rule out the blue curve from the gray points. So this team went back and got way more time with the Hubble Space Telescope to get these black points. These points do have error bars on them. You just can't see them. They're so small comparative to the ones on the gray points. So here we have this panel, a zoom in on the black points. Now you can see the error bars. Same thing, we're fitting a bunch of models. So now we have our 100% water model. We can clearly rule that out. 100% methane model, that really doesn't work. And the 100% CO2 model almost works, but then this kind of fails too. It looks basically like a flat line. Like you've taken all the structure in the spectrum and blurred it out, just made it all gray. So what can take all the colors of the day sky and make it just completely gray? Clouds, yes. These are clouds. The clouds are basically scattering out any structure that we actually have in the spectrum. So this is evidence of clouds on planets outside of our own solar system. Probably not water vapor clouds in this one, but it's probably too hot. These are probably like kind of silicate dust clouds. All right, so moving on, this is how we've been doing stuff, but we are living in a very exciting time. So on Christmas Day, the James Webb Space Telescope launched. So this is our last image of JWST before it went to a very, very dark part of our solar system. It's in a very, very dark part of the solar system, very much on purpose. And JWST is going to be really amazing for characterizing planets. It already is having, you may have seen some of the results recently. I actually showed you one of the results at the very beginning of this talk. And in the early stages of JWST, there's this early release science program I'm a part of. And the idea here was to really test out James Webb's potential. They wanted to get data to the community to really get it in the hands of people, experts in different fields. So there are 3 of these ERS programs that focus on exoplanets or planets in our solar system. So ERS 1366, which is about transit spectroscopy, ERS 1386, which is direct imaging of exoplanets, and I showed you that image in the beginning is from ERS 1386, and ERS 1373, which is about Jupiter, and if you've seen any really stunning pictures of Jupiter, recently they're probably from this. They're really amazing. I'm not going to talk about this because we're talking about exoplanets today, but definitely look at the JWST images of Jupiter. They're really stunning. But moving back to exoplanets, I'm going to show you some of the results first from ERS 1366. So just also to note, a question I get a lot is, so what will JWST do better than Hubble, right? How is it different? And you get these things, you get media reports of, oh, it's 100 times better. Well, what does that even mean? So here's the main differences. HST has a 2.4 meter mirror, JWST has a 6 meter mirror. So that makes a difference, right? Your mirror diameter is going to affect your resolution and how much light you collect. And then the other really key difference is the wavelength range. Hubble is an ultraviolet and optical telescope mostly, and gets a little bit of the infrared. Webb, in contrast, is an infrared telescope, and it covers a lot of wavelengths that Hubble simply does not cover at all. And these wavelengths in particular are very useful for studying exoplanets. So another little just bit of orientation. This is maybe not even the best image for this. JWST has 4 instruments. Here are some alignment images from each. So this is NIRSpec, the near infrared spectrograph. So mostly, this is an image from it, but mostly it takes spectra. NIRCam, their near infrared camera, takes images, as you might guess. NIRI, mid-infrared instrument. So this is the one that's working further out in infrared. And this one works at wavelengths where we just can't access it all from the ground. And the fine data sensor and NIRIS down here, which does some imaging and some spectroscopy. So some of the later slides are going to say, oh, we're using this instrument or that instrument. So just wanted to give you the very brief overview of the instruments of JWST. So back to JWST Early Release Science Program 1366. So this is the very first transiting exoplanet science from JWST. And they're trying all 3 techniques I just showed you. They're going to get a phase curve for this exoplanet, WASP 43b, have gotten actually, I think they have all their data. They're doing transmission spectroscopy on WASP 39b, and these are all hot Jupiter planets. And then they're going to also do a secondary eclipse spectroscopy of WASP 18b. And again, I need to realize that this is also past tense. They have these data already. And in fact, a couple weeks ago, I don't know if who saw the press release about CO2 in the atmosphere of an exoplanet? No? Oh no, really? Okay. Yes, so from this observation, we have the first detection of CO2 in an exoplanet atmosphere, like very strong detection. And again, this is this transit technique. We're looking at the dip in the starlight as the planet passes in front, and the size of the planet at different wavelengths tells us about the opacity in the atmosphere. So what you can see here is at a wavelength where you're not in an absorption feature, the red points. Oh, this is really not colorblind friendly, so if anyone's colorblind, I apologize. I don't think this is very readable. So outside of the absorption feature, the depth is a little less. Inside of the absorption feature of CO2, the depth of the transit is a little bit more. So now we can look at that as a spectrum, and this is the spectrum of this planet from JWST, and a really clear detection of carbon dioxide. in the atmosphere of this exoplanet. And the other thing you can see, if you look at this, look at these nice, beautiful, clean error bars. So I was showing you some HST data here, really chunky error bars. And this is, you can see that this data is just a lot more precise in general. All right, so that is transiting exoplanets. I'm going to conclude the talk with what I work on, which is direct imaging. So there are fewer directly imaged exoplanets than transiting exoplanets. We know of maybe 20 or so. And this is because it's obviously a very technically challenging thing to do, right? It's like trying to image a firefly next to a lighthouse, but you're not sitting on the beach looking at the firefly in the lighthouse. So let's say you're here in Glasgow. Any idea where your lighthouse and firefly would be in this little model?
London?
Close. It's probably about the right distance. London's maybe a little too far. Dublin. Yeah, that's the resolution you need to image an exoplanet next to a star. Plus, you need the contrast. You need to be able to overcome the fact that the star is going to drown out your exoplanet. This is, however, a thing we can now do, albeit still in a fairly limited cases. So here's a nice little gallery of directly imaged exoplanets. So just out of curiosity, before you came here tonight, how many people here knew that you could take a picture of an exoplanet? Yay! Good. Good. Because a lot of people don't realize that. We actually have quite a few. The first ones discovered are these two systems. We, however, give them the most boring of names. So this is HR 8799, this is B, C, D, and E, and this is Beta Pig B. So it's basically the name of the star, and then you just put a letter for each planet. So like the planet I showed you, which is this one here, 65426b, these are all baby Jupiters, right? So they are very young for exoplanets. They've just formed, so they're a lot hotter than they'll be by the time they get to solar system ages, and hence the contrast ratio between the star and the planet is favorable enough that we can image them. These were imaged with 8-meter class ground-based telescopes and chronographic imagers to block out the light. So we have a bunch of kit that we're using to block out the starlight in each of these cases. I'm not going to go into details. So these were discovered with a little less kit. These were discovered in the last decade using 2 planet-finding cameras. One is the Gemini Planet Imager, GPI, at the Gemini Telescope. And the other is SPHERE, which is an acronym, and I don't remember what it stands for, at the Very Large Telescope. Also an acronym, and also reflective of the fact that sometimes astronomers are not that imaginative at naming their telescopes. But so we have, this is just kind of a highlight reel, we have about 20 of these. They're also very wide planets. So this system is very scaled up compared to our own. The star is about 2 times the mass of our star. The closest in planet is about 14 times as far from the star as the Earth is from the sun. And the furthest out planet is about 70 times as far. And the masses of these planets range from about 3 to 10 solar masses. This planet here, Beta Pig B, is kind of like a scaled up version of Saturn. So again, its star is about 2 solar masses, and the planet is about 11 or 12 solar masses, and about 10 AU, 10 times as far from the star as the Earth, and about the separation of Saturn from our star. So we have these, and a lot of what we're aiming for here, while we are studying these baby Jupiters now, we're working on pushing these techniques to lower mass planets eventually, and in the coming decades, eventually to exo-Earths, although that will take space telescopes probably. And the advantage of this technique is that these are pictures, right? And we can take pictures in different wavelengths, we can get spectra, and we can start to learn a lot about our planet. So here's one more example. Again, a baby Jupiter. And here's images in different parts of the infrared. All of these images I'm showing you are infrared images so far, although most of them are kind of in the blue side of the infrared. And here is its spectrum. So this planet was really interesting because it was the first of the directly imaged exoplanets to have this spectral feature. So this dip here is because of absorption due to methane in its atmosphere, which we had expected this class of planet, but for various reasons, this is the first one we actually saw it in. All right, so now moving on to what we're doing with JWST with this. So this is the early release science program that I'm involved with. I'm actually co-PI of it. And we had 68 hours to observe 3 different targets. I'm going to show you results from 2. So one is a young planet, HIP 65426b. This is the one I showed you right at the beginning. This here, BHS 1256b. This is a nearly planetary mass companion. It's less than 20 Jupiter masses, but it's much further away from its star. So this one is within 1 arcsecond, so very close to its star. And I should have come up with an analogy to explain how close an arcsecond is, but I don't have one at hand. But, so within 1 arcsecond, this one is 8 arcseconds away. So comparatively a lot easier to image. Here we've used a chronograph to block out a lot of light. Here the contrast ratio is not so high, and we can just, this is just a picture with a telescope. No additional effort has gone into blocking out the light. So we have these 2. We're also looking at this circumstellar disk around a young star. So all this structure in the circumstellar disk may be formed by planets forming in this disk. And we actually have most of this data in hand, except we're still missing half of this data. We actually had an attempt with the telescope, and the telescope had a technical problem and lost a day of data. So now we have to wait for it to reobserve it in the spring. So I'll show you the other 2 instead. So starting with HIP 65426b, which I've already told you a bit about. So just think of this one as like Jupiter, just much younger, 14 million years old, which is only in astronomy do we call something that's 14 million years old young, but there you go. And 6 to 8 times more massive than Jupiter. So on the right here, this is a color magnitude diagram. So it's a really classic tool that we use in astronomy to understand how we figured out how stars work. But here we're using it to figure out how brown dwarfs, which are the slightly more massive cousins of planets, and how planets work. So all these objects are either brown dwarfs or young planets. And here is HIP 65426b. The key thing to take away, this side is redder, this side is bluer. This one's one of the redder ones here. And what we think is happening, the redder ones here have a spectral type we've defined as L, because we just give them letters apparently. But the key thing about L-type objects is that from their red colors, we expect them to have dust clouds, so silicate clouds, kind of similar to the ones in the GJ1214 planet I was talking about. But it inferred, not measured directly until now. And these ones that are bluer, any given object, as it cools with time, will transition from these redder ones, and eventually will become one of these bluer ones, and these silicate clouds dissipate. And here, when we get to over here, this is the T spectral type, which is comparatively clear atmosphere. It also cools enough that we start seeing methane absorption. So the planet I showed you with methane absorption, that's right here, that's 51 area B. So there's a lot going on in this transition. But remember the silicate clouds, we're going to come back to that. So I showed you our nice picture of that already. Now I'm going to show you what we had to do to get to that picture. So we don't just see the planet pop out when we look at it with the telescope. We have the star to connect with. So again, we're using a chronograph, which is a piece of kit to block out a lot of the starlight. And I could give an entire talk on a chronograph, so I'm not going to. I'm just going to say, even after we've blocked out the starlight, we can't see the planet. Right? So this is what the raw data looks like from the telescope. At 3.5 microns here, at 11.5 microns here. This is with the NIRCam instrument. This is with MURI. And we're using 2 different techniques to detangle the planet from the starlight. The first one, that stands for angular differential imaging. What we do is we take 2 sets of images. Here we have the planet at one angle, and then we basically roll the telescope and take an image of the planet at a different angle, and use that to subtract out, to model and subtract out all of this messy starlight. So that's one technique. And this technique here is reference differential imaging. And what we've done here is we've taken images of the star and the planet, and then gone and looked at another star. and use that star basically as a reference to figure out what the starlight is doing and subtract it out that way. And one interesting thing we learned here is that for this particular case, we thought these were both going to work equally well, but the reference differential imaging actually worked quite a bit better than the angular differential imaging. So we didn't really get a gain doing both compared to just doing the reference differential imaging. So you might also be wondering, why does this look like a little snowflake? And the answer is, so this has to do with the shape of the mirrors on the James Webb Space Telescope. So it's not just one big mirror, it's like a bunch of hexagonal mirrors. So this is basically the imprint of the fact that you have these multiple mirrors on what the images from the telescope looks like. So here's our picture. What science do we get from this? So the key thing here is that, oh, and here's more pretty pictures actually. So this is all of our set of pictures. So we actually took images from 2.5 microns here out to 15.5 microns here. So we are covering pretty much all of the infrared. And again, anything past 11.4 microns, this is the first time we've ever imaged an exoplanet at these wavelengths. So these other wavelengths at 3.5, 4.1, 4.4 microns, we have some images from the ground, but these are really bad wavelengths to try to be working from in the ground. So you've probably seen pictures from infrared cameras, right? And if you look at your image from an infrared camera, you're glowing, right? Because humans, the air, your telescope, your camera, at room temperature, if you look at 5 to 10 micron images, everything is glowing. That's basically the peak of our black body radiation. And that's the main reason James Webb is out at the Lagrange point, far from Earth, where it can be kept very, very cold to keep it from glowing. And so that opens up the possibility of imaging at these longer wavelengths and really improves our ability to image at wavelengths from about 3 to 5 microns as well. So what can we do with this? So the main thing is that we are now covering all of the wavelength ranges where this hot, warm planet outputs light. So given its temperature, its black body peak, the peak of its radiation, is right here in the near infrared. It doesn't have a lot, if you look blueward into the optical, it doesn't produce a lot of light. If you look redward into the radio, it also doesn't produce a lot of light. Here it's pretty much covering everywhere it's producing light. So this spectrum here is from the sphere instrument at the BLT, and these points here are our new photometry from the James Webb Space Telescope, and here we just have a model, a possible model atmosphere. But what you can see is that we're really covering all of the light produced by this planet, which means that we can estimate its total luminosity very accurately. And once we can do that, that allows us to improve our estimates of mass, temperature, surface gravity, so essentially how dense it is, and radius of the planet. So this is using a model. So we have a model of how a planet should cool with time. So at a given age, at a given luminosity, the model gives us an estimate for mass, effective temperature, surface gravity here, and radius. I won't get into the details of exactly what we did here, but basically, our mass range for this planet is 7 plus or minus 1 Jupiter mass, and it's actually pretty puffy, right? So its radius, that is wrong, that should be the radius of Jupiter there. It's 1.45 times the radius of Jupiter because it's a young planet and it's still contracting. It'll eventually get to be about the same size as Jupiter. So one of the big science result from this was essentially that we were able to really constrain the mass of this planet a lot more accurately. Okay, so the other cool science result is because we can work much more effectively at these longer wavelengths, if there had been a Saturn mass planet in this system, we should have been able to image it. So what this is for this observation, as a function of the distance from the star in astronomical units, where 1 astronomical unit is the distance between the Earth and the Sun, and the mass of the planet Jupiter masses, especially at 4.5 microns, we could have gone down to Saturn mass planets at fairly wide separations. So again, this is just, JWST is really exquisitely sensitive. All right, so I also want to tell you a little bit about VHS 1256b. So very similar sort of object, to HIP 65426b, we've just pulled it a bit further from its star, so it's much easier to observe. And so this here is the first spectrum of a nearly planetary mass object with JWC. It's less than 20 Jupiter masses, so all the way from 1 micron out to 20 microns. So this is just, this data is actually just really exquisite. I could zoom in to many parts of this spectrum, and you can just see there's just so much detail. We've seen so many different features from so many different molecules we haven't seen before in these planets. And of course, this whole range from 5 to 20 microns, we've never had a spectrum of a planetary mass object at these wavelength ranges. So this is the very first. I'm not going to go into any real detail on this one. I'm just going to show you one little highlight. So I was mentioning that we inferred the presence of silicon clouds from the red colors of this object. But the spectrum actually produces some direct evidence for silicon clouds. So right here, this little dip is due to silicon clouds, dust grains in the atmosphere of this planet. So here we're comparing our planet with a brown dwarf that doesn't have this silicon feature. Here it is compared with the planet with a brown dwarf that really, really has a silicon feature. And this is the first direct detection of clouds on a directly imaged exoplanet. All right. I should also note, and I'll kind of end with this thought, this is my last kind of chunk, that this object is also highly variable. So this is data from the Hubble Space Telescope over 8 hours, and you can just look at this one from 1.1 to 1.7 microns, but over 8 hours it changed by nearly 20%. It got 20% brighter. That was kind of wild, but in fact this class of planets and brown dwarfs tend to have this high variability, although this is the most variable of them. So what's going on here? This is also evidence actually for patchiness in the clouds of this object. So what is making it get so much brighter, so much faster? And the answer is we are probably looking at patchy, like holes in clouds, like surface features essentially. So we have the benefit of being able to just resolve Jupiter very easily, but here's what happens if you take HST data of Jupiter and de-resolve it and look at how it would look as a function of time. So basically make a light curve like this one, but with Jupiter. Now we're looking in the optical here instead of infrared, but what you can see is you see variability, right? And you also see that it repeats. So what's going on here is we're seeing the cloud features of Jupiter. We're seeing parts of Jupiter that are a little brighter or a little fainter because of the clouds, and it repeats every time Jupiter rotates, which is about 10 hours or so, right? So we can essentially figure out what the cloud features of these objects look like and get their rotation period by monitoring their light curves like we've done with this one. So, one issue though, if I just say, look, it repeats, we have one period, we've made an implicit assumption. We've assumed that Jupiter rotates like a ball, right? So that it's just like if you took a bowling ball and had it rotate around and all parts of it kind of rotate in a rigid way. But as we know, Jupiter doesn't do that, nor does the sun, nor do most astronomical objects. They are differentially rotating. So if you wanted to measure a rotation period for a differentially rotating object, how would you do that, right? And the answer is you actually would get more than one. So for Jupiter, if you measure its rotation period at the pole, it's 9 hours and 55 minutes. If you measure at the equator, it's 9 hours and 50 minutes, so a 5-minute difference. And that's just watching when clouds come around, essentially, at each of those different latitudes. Now, you can also measure the period via the magnetic field. So Jupiter is a very prolific radio emitter because of its interior magnetic field. It also produces radio pulses, and the period, if you do that, is 9 hours and 55 minutes, so it's that slightly longer period. So what's going on here? So what's going on is that you're actually seeing the wind speed on Jupiter here. So the radio is following the interior The optical here is following the atmosphere, right? If you subtract the two, the difference is the wind speed. This is my one equation, I promise there's no more. And if you have an estimate of the radius, yeah, you can calculate the wind speed. So why am I bringing this up here? This gives us the ability to measure wind speeds also for planets outside of the solar system, or in this case, the brown dwarf. So again, brown dwarfs are the slightly more massive cousins of planets, in between stars and planets in terms of mass. So this one has, that's T spectral type I was mentioning, where it has clear comparatively clear atmosphere and nothing absorption. It has an estimated mass of 16 to 68 times the mass of Jupiter, and it's a very fast rotator. So even though it is more massive than Jupiter, it rotates every 1.77 hours. So it's flying around less than 2 hours. So what we did was try to do the same thing. So we measured, instead of working in the optical here, because brown dwarfs are quite faint in the optical, we measured the atmospheric rotation period in the near infrared using Spitzer when it was around. And this is our light curve here. So you see it's really regular. We see a really sinusoidal period. And we measured a lot of periods. So we estimate the period from the near infrared variability. We try to do this very, very accurately. Then we went to the very large array and estimated the interior period from the radio. So it pulses basically once every period. So we measured that. And then subtracted the two. And you have to measure your period very accurately to do this. So in fact, the infrared period is very slightly shorter than the radio period, so that's because the wind is mostly equatorial. We can estimate the radius of the brown dwarf from our understanding of brown dwarfs. And so the wind speed on this dwarf is 650 meters per second, which is not surprising, right? So this is something that is about the size of Jupiter, but is rotating 4 times as fast. So it's not surprising that it has really strong winds. So one exciting thing we're trying to do is we have a couple more targets for this. We're going to be proposing for JWST time for this. One of our targets is actually a planetary mass object, although it's not orbiting a star. So hopefully some more measurements of that soon. So I hope I have convinced you that there's going to be a lot of very exciting results, largely from JWST, but from a lot of sources coming soon. And I will end where I started with the first JWST image of a planet. Thank you, and I'm happy to take questions.
Thank you very much, Beth. That was fascinating, and every time I hear about exoplanets, I'm actually gobsmacked at how much further we've got, and you've got, because you've presented some of your own results here, which is just marvellous. You mentioned arc seconds. If I got my sums right, an arc second, to give it some local context, would be somebody holding up a coin while standing down by the Clyde, as viewed from about here. That's about the size of an arc second. And what were the resolutions that you were looking at and the sizes?
So this planet is about 0.8 arc seconds from its star.
Okay, that's small. Yeah. So, any other questions for Beth?
I was wondering, is it enormously difficult to get time on these big space telescopes? But most of the stuff you're talking about has been by very ingeniously bringing all the data together. When you're saying you're hoping to be able to get extra data from JWST, etc., is there a new system that's come into play whereby you actually sort of get priority to use different telescopes at the same time, or to get the data, or is it just all public source data?
You just have to go and compete for it. So this ERS observation, back in 2017, we organized our group and we put in a proposal, and there were probably like about 100 or so proposals, and 13 of the proposals got time to do this ERS science. A lot of the others got recycled and were successful in cycle 1. So the way it works is, in most cases, you submit a proposal, it goes in front of the panel, and you wait and see what happens, and then in many cases you resubmit it, and after that you resubmit it again, and maybe sometimes it gets time.
Can I ask a question? I'm curious, what do you think the actual smallest planet that James Webb Space Telescope would actually be able to detect
Depends on what technique you're talking about.
Well, I mean, actually, to see, I know that Edinburgh is bright stars, but I mean, what's this kind of limiting magnitude, if you like?
Okay, so using the transit technique, James Webb, there are a few very like Earth-sized planets that could be observed with the James Webb, but they are the ones that are also transiting very small stars. But for this technique for direct imaging with the James Webb Space Telescope, it's going to be things that are more massive than, well, actually no, we can go down to maybe Neptune mass young planets with this kind of imaging. Let's do these two.
I have another question. Is it when you were talking about the radial velocity method, when you talk about big planet, how do you distinguish if there's like maybe 3 or 4 big planets going around? I mean, you talked about, you know, but I mean, what for the 5 big planets going around? How would you distinguish that?
Okay, so usually what people do with radial velocity, they have their data, and they have, you know, the radial velocity curves, and you wouldn't necessarily, the one I showed you, you could really pick out the planet easily. You aren't necessarily able to do that. So people use a periodogram to estimate what periodicities they have in their planet. So they'll basically say, oh look, this one has a period at 100 days. Then they'll look at that, you know, take that period out, and then they might find, oh, there's another one at 20 days. And they just keep on going, basically subtracting out planets until there's no more planets to find. So that's usually how it works with RV, with the radial velocity technique. However, you have to be very careful about this because there's been some planets that are claimed that then quietly went away because they had actually kind of over-subtracted from their data, and so this planet signal wasn't really there. So you have to be very careful of that.
Did they really go away?
There were some planets that are published that are not planets, yes.
What about gravitational pull amongst multi-planets, extraterrestrial planets? Gravitation?
Yeah. That can have some significant effects. So for instance, if you have a system with multiple planets and they transit, the tugs of the other planets can change the time at which you see other planets in the system transit. So those are called transit timing variations, and that's a direct result of the other planets tugging on each other.
So there's a member of the team just looking at that amongst all the other things you've done.
There's some techniques. Well, the thing about the field in general is there are so many ways to study exoplanets. It really is, you know, a huge field all on its own. And the stuff I'm doing here is so distinct from what the transit community does, or what the radial velocity community does, or what the microlensing community does.
We have a question here in the middle at the front.
You mentioned the hot Jupiter was going to get smaller, it was only 14 million years old. How could you tell the age of it?
Oh, good question. Okay, so how do we know this one is 14 million years old? We know it, maybe I don't, I regret my choices. Here we go. We know it's 14 million years old because it is a member of a young association of stars. What that means is it has a lot of friends near it, and they all formed in the same star-forming cloud. And if you look at their motion on the sky, they have similar motions because they all form in the same part of the cloud. So essentially, because this object is moving along with these other young objects, that's how we know that it's
Question. You mentioned a tilt of the spacecraft.
Yeah.
Would you like to elaborate on that?
Okay, so rolling the spacecraft.
Rolling it.
Yes.
I mean, I would have thought when it went round at the Lagrangian point, it would change its attitude towards the target. But you're saying you have to...
You can change the angle that you're looking at the target just a little. One reason that technique didn't work as well as we expected, well, is for a completely expected reason. You can't change it very, very much. So we use that technique from the ground as well, but we usually roll things by, like 30 or 40 degrees on the sky. JWST can only roll by 5 to 10 degrees, so it's just not a lot.
Good.
So those images that you were mentioning of Jupiter from the James Webb, are those then not true colour?
No, they're not, because they're all infrared images. So they're not wavelengths that you can see with your eye. So they've translated the colors to optical wavelengths so that we can look at them. So it's combining images at different wavelengths. So it's like how you make a 3-color image. So if you had a red image, a green image, and a blue image, you could combine it together to get a 3-color image. But essentially we have a black and white image at each of those wavelengths, just showing the intensity of light, and then we're translating each of those to a color that we can actually see with our eye.
In one of the early slides, am I right in reading from it that the James Webb Space Telescope is actually blind in the blue?
Yes.
So it can't see the short wavelength end of the visible spectrum at all?
Not at all. It can't go past 0.6 microns.
Okay, so that's, in one way, our telescopes are better than the James Webb.
Yeah, and you know, the only telescope right now that can work in the ultraviolet is the Hubble Space Telescope, so it's still has a quite unique and important capability. Like, it's not that James Webb makes Hubble obsolete, they're really complementary.
This will be a daft question, but I mean, I'm into television and video and all the rest of it. I can't help notice VHS, video home system. So why is the planet named after a video system?
It is the VISTA hemisphere service. So VISTA is a 4-meter telescope at the same site as the very large telescope that's done a lot of infrared surveys of the southern sky. And again, astronomical naming conventions are basically either, like for a star, it's basically the survey that detected it and a number. So PHS 1256 minus 1257 is the survey it's from, its right ascension, and its declination. And that's it. We don't get to call them fun names, unfortunately.
That we got rubber VHS. I know that. So, can I just, talking about in ultraviolet there, to me, I was probably sleeping at the time, these are brown dwarfs and red dwarfs. Right. Yes?
Okay, so the line between brown dwarf and planet is really, it's fuzzy, right? So nominally we say something that is more massive than 13 Jupiter masses is a brown dwarf, and something less is a planet. But that boundary, what that is something that's greater than 13 Jupiter masses has a very short phase in its lifetime where it can burn deuterium as energy, and something lower than that can't. But is there a big practical difference between the two? Not really.
What about the primary star throwing off atmosphere or whatever? I know some of these planets are well out.
Yeah, some are. I mean, I've kind of shown you two classes of planets. So this one is well away from its star. So it's basically unaffected by its star in many ways in terms of its properties. But the hot Jupiters I was telling you, yes, they're strongly affected by their stars, and some of them are being evaporated by their stars.
That's going down.
Well, yes, but slowly.
I'd just like to say, from my point of view, my head hurts, but in a good way.
Can I keep that quote?
Thanks.
On the next
More
book,
questions coming from the back.
Yeah, I was wondering, how long does James Webb need to stay at these points in the sky to get a good amount of data? Like, how long does it look at one point?
That's a really good question. So it really varies. So this spectrum took 4 hours altogether to get, whereas these images, all of this, to get this probably took about 30 hours, where half of that was actually getting these images and half of that was looking at reference stars.
Okay. Well, if that is all the questions, can I ask you to thank Beth once more for her explanation? And I hope to see you at one of our upcoming events. Your first chance to see our observatory, which will not be fully functional, will be at the Mugdock Observing Night on, is it the 18th of October? Yes, Tuesday the 18th, so it's the third Tuesday of the month. We'll try and keep that going through the winter season as well. Okay.